Okay, hello everyone. Welcome back to my YouTube channel and welcome to this video. Today I have a very important topic for every one of you interested on learning about techniques, methods related to hardware in the loop and real-time simulation. Today I will run a short introduction about an application developed by Typhoon HIL that received the name Virtual HIL device. This introduction is intended to clarify and make easy to understand what the Virtual HIL device is and how to use it. Well, but before we start with business, I would like to make a short introduction. I would like to tell you that I am creating those videos in order that people can easily learn or speed up the learning curve. However, my videos, my documents are not intended as substitute of the official documentation created by the manufacturer. As I say in every single video, I totally suggest that the viewers please read the proper documentation created by the official manufacturer. They provide a comprehensive information, very simple to read and very simple to understand, okay? Couple more things before we go into full details. I would like to recognize the effort of my master student, Mr. Usair Latif. He is a master student in power system and he has been helping me creating documentations about Typhoon HIL elements and devices, okay? And finally, I would like to acknowledge the collaboration that we are establishing with Typhoon HIL. Thank you to everyone working on Typhoon HIL because they are being very supportive in this activity. Thank you very much. Okay, but let's go for business. I must talk about Virtual HIL. And to understand what is Virtual HIL, I think it's very important that people must be clear about several concepts, especially concepts like hardware in the loop and real-time simulation. In this sense, I decide to use an example. Imagine that you are interested on developing a one-pack, a wide area monitoring, control, and protection system, okay? Imagine that your task is developing this cyber physical system with some hardware and some software, okay? But as you must be aware, when we are working in wide area applications, we need to have signals coming from the real power system. Signals like voltage and currents that they can be in the form of communication protocol like the IEC 61850 or something like that, okay? But also, we have communication between the one pack and the physical relays at the field. What I'm trying to say is, in reality, when we are developing a one pack, we are interacting with several cyber physical environments, okay? And the bad news here is a one pack, for instance, if we are talking about early instability detection, that means that if we are interested to test the one pack, we need to have signals coming from an unstable system in order to prove that our one pack is detecting the situation. And the bad news is that the TSO, transmission system operator, will never agree that we put down, create a blackout in the power system in order to get the proper signals related with the blackout and demonstrate that the one pack is working. What I'm trying to say is that testing this kind of cyber physical systems is very, very difficult, okay? But imagine the following. Imagine that we are interested in developing this one pack, but at one stage of the developing process, we would like to know what is the response that the physical protection relay has when this one pack is working with the power system and closing the loop with the physical relays. Well, to solve the complicated situation related with testing this kind of cyber physical systems is when hardware in the loop simulation is very important. I must be honest, hardware in the loop is not a new technique. It's been in the market for many years, especially in the automotive industry, aerospatial industry, and many other areas, especially in control systems. Just recently, a few years ago, we started to use hardware in the loop for power system. And what I need that you understand is the hardware in the loop is one technique that is used to develop and test complex real embedded system. Okay, for instance, one pack is a real-time application. The one pack must be receiving signal from the power system, and depending on those signals after an assessment, the system must provide a response. But this response must be in real time, must be in that way that is at the moment that is needed. For that reason, real-time applications must be assessed in a different way. Real-time applications, one of the critical aspects is the time required to get the response from the system, okay? Well, but here I am trying to show you the very basic example that I started below. Here I am showing you the classical hardware in the loop testing implementation. In this case, we are interested in the behavior of this protection relay. And to protect and to see the response of that protection relay, we need signals. Signals coming from the one pack and signals coming from the power system. Now we say that we have no access to the power system, but we develop the one pack. Well, the solution is very simple. Use a cyber physical system that allow me testing this hardware in a closed loop. And that is where real-time simulator take place. The real-time simulator, you can imagine the real-time simulator like a very powerful computer, a very fast computer designed for modeling and simulation in extremely fast way with high fidelity. The real-time simulator is typically like a classical computer, and there is a CPU inside, but also there is a very dedicated hardware that allows the acceleration of this kind of time domain simulation, and that is the job of the FPGA. Of course, to control the real-time simulator, we need a workstation. And inside this real-time simulator, what we are doing is inside a cybernetic environment, we are creating the model of the power system, the one pack that we are developing, and we are sending signals from the real-time simulator to the real physical relay to test the performance. And that is what I am representing over here, okay? However, what is one of the big issues? Okay, real-time simulation is very different to offline simulation. Offline simulation, time is not a problem. In real-time simulation, hardware in the loop, time is a very important issue, okay? That is the reason that we need to use this supercomputer, let's say very fast computer, the real-time simulator, okay? But those real-time simulators can be expensive. And that is where Typhoon HIL creates something called virtual HIL. Virtual HIL is not an offline simulator. It's not at all. Why not? Because virtual HIL is replicating the functionalities of the physical computer and the hardware involved. That means that virtual HIL in reality is a virtual machine, a concept that is taken from the computer science and allow in one computer running with a CPU having the full chain of testing hardware in the loop. That is the virtual HIL. The virtual HIL device, that is the name created by Typhoon HIL, is basically a software tool chain that is allowing you to learn, to speed up the learning curve of hardware in the loop and real-time simulations. But the critical point is that you will not be using a physical real-time simulator. The virtual hardware in the loop, the virtual HIL, what it's doing is using this virtual machine to replicate all the behavior that you will have when you are running real-time simulation and hardware in the loop. Of course, the good news here is that you will learn all the principles and the technique used in hardware in the loop, but without the concern of using a real software. Of course, there are some limitations, but we will discuss that later. Probably you are wondering, okay, why using virtual HIL is very important to understand hardware in the loop. Well, one of the things that I need that you understand is that using virtual HIL devices, you must have and learn, you have the opportunity of learning and experiencing all the factors related with the real implementation of a hardware in the loop. And that means challenges and of course advantages. Challenges. When we are running real-time simulation, the real-time simulator hardware is a very important aspect. The real-time simulator have a very important activity, but facing a very important challenge. In real life, when humans receive an excitation, they think about and they produce a response. What I'm trying to say is the human being have an input, the human brain do some calculations and then create some outputs. In terms of time, it's almost instantaneously. But that is not the case when we are working with computers. In real life, the time is a continuous variable. But inside the computer, the time is a discrete variable. And for each procedure, for each moment, let's say this very small moment here, the time that is elapsed over there is very important because we need to run some calculations. For each moment here, we need to run some inputs, run some calculations, and get some results. And that must be done in a very fast way. Why? Because we have only this small window over here to collect the results. And that is the reason that the real-time simulator is using a very powerful hardware, a CPU that is used basically for calculations related with slow processes. For instance, measurements. But if we are working with models, very complex models with very small time constants, for instance, power electronic switches, we need a very fast calculation. We need a lot of intensive calculation. We need something very fast, and that is the reason of using the FPGA. What I'm trying to say is for this very small instant, the CPU is running these three things: input, computing, and output. However, inside those steps over here, we have a very small time scale where the FPGA is running very fast calculation in order to complete on time all the calculations and getting the results. Well, this explanation is very basic, but what I need that you understand from here is when you are using real-time simulation, the hardware is very important. The selection of models, selection of time constants, selection the way that the model will be solved inside this very expensive hardware. Well, the virtual HIL, this virtual machine from Typhoon HIL that I am talking about, it has the possibility of replicating and exposing you to all those challenges, and you will take the advantage of learning all those things without having the real hardware. What I'm trying to say is the HIL device, the virtual HIL device, offers you several advantages. You don't need the real-time simulator because virtual HIL will have the CPU and the GPU inside your computer using your CPU. But you will learn all the tool chain that you require to perform hardware in the loop. Also, you will be able to develop simulations and verification models that later, if you want to run inside a real-time simulator, you just need one click and you will run the real-time execution inside the real-time simulator. What is the consequence of this? Well, you will learn extremely fast how to develop model, how to test, independently of the real-time simulator that you are using. And more important is, at the end, you will be able to develop your models and you will understand the whole tool chain. And from there, you can use those models that you create inside the virtual HIL device and use in a real-time simulator in a real Typhoon HIL device. That is extremely important, okay? Well, how Typhoon HIL reached this virtual HIL device? Well, the virtual HIL device is a consequence of a development of Typhoon HIL from this important software that is called the Typhoon HIL Control Center. The Typhoon HIL Control Center is the application controlling all the different applications that you need to do in order to replicate the software tool chain for hardware in the loop and real-time simulation. For instance, this is an example of the Typhoon HIL Control Center. When you download the Typhoon Virtual HIL device, you will receive this. And there are some applications like the schematic editor that will allow you to create your models. And then you have the HIL SCADA that will allow you the communication between the model and some gadgets to get information or some devices to get action, okay? Typhoon HIL uses in the control center an approach that is called model-based system engineering. What this means is that the MBSE is an application of modeling in order to help you in the requirement in all the stages in a system project: requirement, design, analysis, verification, and so on. Here you have a short diagram showing you the several steps during the developing of a system engineering project. Here at the very early stages, system requirements definition, of course you can have some troubles. And if you have those problems over here at this stage, of course, the economical impact is very low. Then we start with the implementation, building the prototype. And if we have a mistake, this can be expensive. But the worst case scenario is if you have an error or a mistake during the test and evaluation, that will be a disaster. Hardware in the loop, the virtual HIL device, allow you to perform assessment in all these change at all the stages and allow the user to detect early errors and mistakes and of course create solutions. That is the key point of using the model-based system engineering toolchain, okay? If we look over here, or very early example, you can see that we can start the development by using a cyber system, and that is using offline simulation. We can define the system requirements, we can think about integration, but everything is offline. Then there is the next stage. We can go to the cyber physical system where, for instance, we have the whole power system, the one-pack inside the real-time simulator, and we are assessing the performance of those protection relays when the one-pack is working. And then we can assess if the protection relays are able to work properly with the one-pack. If this stage is successful, we can go for the full implementation, and then the one-pack will be implemented in hardware and software. The one-pack will be a cyber physical system. But now, when the hardware and the software of the one-pack is ready, we need to test that the one-pack is properly working. And now what we will do is, here we have the one-pack as a physical prototype, and we use the real-time simulator to replicate the behavior of those relays, what we call the virtual relay, and of course the power system is inside the real-time simulator. Again, this is a physical cyber simulation. The end of our one-pack project will be the very last stage, and that is the physical validation. The physical validation is installing the one-pack with the relays and receiving the signal from the real power system. What I'm trying to say is that virtual HIL is using the MBSE approach that allows you to test in many different stages your models, your prototypes, your physical components, and your cyber physical components, all of them. And that is very important because the MBSE approach allows to reduce the risk of making a mistake or a potential failure and accelerate the project speed. Also allow to detect a very early stages, interoperability issues, and of course, at every single stage in your development, system development, you have the opportunity of improving the functionalities of your system. Okay, now we are reaching the end of this video. Again, this video is intended to show you a very important tool, the virtual HIL device created by Typhoon HIL. The virtual HIL device has several features. One of them that is extremely important is for free. Yes, it's for free. You can download from the Typhoon HIL website and it's free. The only thing that you need is registration. And the virtual HIL device will allow you to have the full experience related with real-time simulations, all the challenges and all the advantages, and hardware in the loop. What is my general conclusion here? You need to have a test of this virtual HIL device, okay? In my next video, I will show you how to get the virtual HIL device, how to install the HIL device, and few more videos I will be teaching you how to use the virtual HIL device and the whole tool change of the virtual HIL in order to perform hardware in the loop and real-time simulations. Well, this is the end of this very interesting video. I hope all of you enjoyed this video. If yes, please subscribe to my YouTube channel, drop me an email, and I will be very, very happy to be in contact with all of you. Well, that is all for today. I will see you at the next video. Thank you very much.